Great. So next, let's look at some examples of how you test assumptions in linear regression. There's a little bit more involved in looking at assumptions for regression than the other analyses that we've looked at so far in this class. It's kind of a long list to go through, which is part of why it's its own video here. So we're going to be doing some model checking, which you might also refer to as diagnostics in other circumstances, where we're going to be running the model, and then we're going to see what problems are there, because in practice, usually there's some sort of problem that we want to understand. You want to, first of all, be looking at the residuals, which is everything, all the variance in Y that we're not accounting for with X. So there's a few different types of residuals: ordinary, standard, and studentized. In practice, you don't have to print out the residuals yourselves, but I'll just run through them to give you a sense of what's going on. So there's 3 different types of residuals. You don't need to know the difference between all these residuals. I'm not going to test you on any of that because that's getting into the weeds a bit, but I will quickly show you what these look like. So I'm going to print all of these out. You will see that when you get the residuals for regression 2, this will give you 100 different values, and this is how far each of the values for Y are from the regression line. So these will range in value. Some of these will be very small, in which case they're really close, so like 0.2. Some will be very far away. So like the 9.1 seems to be one of the furthest ones away. So in general, the further your values are away from the regression line, the worse that your model is in explaining variance in the outcome variable. You'll see that there's some differences in how what values you get for these residuals. So like -2 something for this one, -0.4 for this one, because this has been standardized into a z-score. And this is studentized, converted into a t-score. But essentially, this is telling you how far away are each of those scores from the regression line. So there are some assumptions about those residuals that we'll want to be taking into account. So we don't want to have any outliers that might be impacting the results. And we don't want there to be outliers in the residuals. That is, we don't want there to be any cases where the value is really far away from the regression line, whereas all the other values are very close. Because what that can do is that can make it such that that slope is actually changing a little bit, like it might be really steep, but only because there's one value that's really far off. If we didn't include that value in, the slope would be a lot flatter, in which case we're concerned with bias. So for this, we can look at leverage, which gives us an indication of how much the values influence that regression line. So this is going to give you a value for each of these points for how much that's influencing the regression line. So if you wanted to, you could look through this. You could then also run a sorting function on this as well to put them in order and go through and see, okay, is there any specific point that really stands out from the regression line that is very different and is not being predicted very well? In which case, that is something that you might want to account for. So for example, you might want to do what's referred to as a sensitivity analysis and run the regression line such that you have the analyses with that problematic data point in there and without. And if the results stay consistent or pretty close to consistent, that's not a problem. If the results change, that is a limitation and something that you would want to report in your analyses. So you can also look at the Cook's distance, which is telling you how far the outlier is away from that regression line. So you'll get a quick distance value. So this isn't how much it's influencing the regression line, but just how far away it is. And again, if you wanted to, you could look through this and sort and see maybe if based on this value, there's something that is extremely far away. You could then, again, do a sensitivity analysis and check those analyses as well. So rather than looking through all of those numbers, another thing that you can do is plot the residuals. So I'm going to do that a couple different ways. So doing this types of visualization often is an easier way to make sense of your data rather than looking through those individual values. So for this, you have a histogram of the residuals. You want the residuals to be pretty close to normally distributed, and you want it to also not have any extreme outliers. So for this looks like a fairly close to normal distribution, not too bad. And there's values that are a little bit out here, but it's not completely separate from it. So maybe we want to take a look at those specific values, figure out what those values are, and see if there's any problem there. But overall, this doesn't look too bad. You can also do this type of plot, the QQ plot. And again, what we're looking for here is we want it to be pretty close to this line, and we don't want any of these to be like way above or way below this this line right here. Again, this is not too big of a problem in terms of any outliers for the residuals, just based on looking at this. So if I found this in my own data, I'd be pretty happy that there's not too much to worry about. And the nice thing about the QQ plots is it tells you the participant number. So this is the row. So you'd want to look at row 36, 78, and 81. And those ones might be the most extreme outliers, if there's any outliers at all. In general, both of these plots look fairly good. So you can also then, after that, look at that assumption that the relation is linear. So if there is some relationship between the two variables, but the shape of it isn't linear, the linear test is going to throw things off a little bit. So for this, you can look at how closely the values fit to that regression line. So what we're going to do here is we're going to create y hat.2, and we're using the fitted values function on that second regression. So this is trying to tell us how much those values fit to that line, or how much they don't fit to it. So we run this function, and then we're again going to run this plot here. So for this, what we're seeing is the relation between the fitted values and the observed values. This, again, you'll want to see a pretty roughly horizontal line. Let's also run regression 2. And this shows you that line. And this basically flattens out the regression line so that rather than it being on that angle, it's like this. So here we're seeing that although it's pretty close to flat, if you just glanced at it, you probably wouldn't be able to see much. The red line here, if this is more curved, this suggests that it's more curvilinear. This might suggest a curvilinear relation between the variables that's not being accounted for. Again, if it's like way up here, that would be maybe more of a problem. You can also look at the plot of the residuals. And so when I run this, what you're seeing is all of that information kind of plotted at the same time, where you're seeing here that the residuals, there seems to be some indication that maybe there is a curvilinear relationship. So this might be a slight problem, I, again, would not be especially concerned with this because real data that isn't like made up for the purposes of running through for a class usually look a little bit messier than this. So again, yeah, you can use all this information for diagnosticity tests. So I'm just going to get rid of these so that we don't run into any problems with those sitting in the background and not having anything run correctly. So again, you want to look at the homogeneity of variance assumption. And so with this, you can plot the data for the regression and see whether there seems to be a homogeneity of variance. Again, you're looking for a flat line in terms of the value and the value of the residual, whether the variances seem to be equal or not. So just glancing at this for the homogeneity of variance might be a little bit unclear. So one thing that I would do is actually run a hypothesis test for the homogeneity of variance, similar to what we did with the Levene's test with the t-test and the f-test. So for this, I'm going to pull up the library car. I'm also going to pull up LM test because we're going to do something from that package as well. Okay, so I've already ran that, but if you're running that yourself, you'll want to install that first. I'm going to pull up the library LM test so that we can use that. So first of all, let's get rid of this, give ourselves a little bit more space here. So you can run the NCV test, and I'll run this here. Let's just move this around a little bit so that it's a little bit clearer. So for the NCV test value, this is whether there is a difference in the variances. And this is going to give you a p-value that's not significant. So the NCV test is one that you can use. You can also run this for the coefficients. If this suggests that the homogeneity variance assumption is not met, and specify VCOV equals HCCM. And so this is using something that's referred to as the variance covariance matrix, something that we haven't talked about that's running in the background. But essentially, this allows you to run the analysis not assuming homogeneity of variance, and you will still get this output, but it will be accounting for that. So that's something that you can do directly. Another thing that you can do is look at whether there is collinearity. So collinearity means that the predictors are really strongly correlated with each other. So one of the things that you can look at is how strong the correlation is between the variables, but you can also look at the VIF, which is the variance inflation factor. So this will tell you how much there might be inflated values because your predictors are correlated with each other. So when you get this, you get invariance inflation factors for these two variables. And that will give you 1.65. Generally, we want the VIF to be below 10, so this doesn't look bad at all. So collinearity is usually not a problem if you only have a small number of predictors. And in fact, you have no worries about collinearity if you only have one predictor. If you have more predictors that you're adding in, there tends to be more and more problems with collinearity. There's more overlap in the variance between the predictors, so there's more of a chance that that will produce bias. You could look at the correlation among all the variables. And one of the things you can look for is, okay, maybe if any of the correlations are above 0.9 or below negative 0.9, we might be worried. So this is something that I look at and say, okay, I want to check the variance inflation factors if I'm going to be running this. Let's do regression 3, which is putting in 3 predictors. And then we look at the variance inflation factors for each of those regression lines. So what we see here is that there seems to be some inflation of the variance. So here, 6.1, here, 5.43. So if you're looking at Dan Sleep and Dan Grump, those two are pretty strongly correlated, and those two also have fairly high variance inflation factors. So like I said, when I'm doing research, I usually look for no variance inflation factors greater than 10, and I'm not worried. So this is a little bit of inflated variance. It's not ideal, but again, it's not too bad. So with this, if you do run into this issue, you can maybe remove predictors if there's ones that are very strongly correlated, and not have as many things in the model. That is the most common way to handle that. Or if you have two predictors that are like 0.99 correlated with each other, you might want to combine them into an index because it seems like they're measuring almost exactly the same thing. And rather than put them in as like competing predictors, they're all part of one larger thing. So when you're doing these diagnostics, looking at the output of the model, usually you're going to run into some indication that there might be some problems with the linear regression. And usually that's okay. You just want to be aware of any of those issues. And if there's anything you can do to account for that, account for any of those problems as best as you can. So next, in the next video, I'm going to talk a little bit about model selection and how you do that.